In this lecture, we're going to look at galaxies beyond our Milky Way and how the universe developed over time. A galaxy is basically a group of stars, gas, and dust in space. The number of stars in a galaxy varies greatly, from just over a few million to up over a trillion. Our Milky Way has billions of stars, so it's pretty average. We can estimate the number of stars in a distant galaxy by the size and brightness of the galaxy. It isn't possible to count individual stars as far away as other galaxies are. These images are all photos of objects within Charles Messier's catalog. We talked about Messier briefly before. His catalog is a list of dozens of objects he found in the sky while looking for comets. You may notice that many of these pictures show types of objects we've looked at before in this class. You see globular clusters, open clusters, emission nebulae, planetary nebulae, and spiral galaxies. There are also other types of galaxies beyond just spirals. People in Messier's time, though, did not understand that these other galaxies were not part of the Milky Way. They just thought that galaxies were nebulae within the Milky Way. In 1920, the National Academy of Science hosted a debate about what they called spiral nebulae, challenging people to argue whether they believed these objects were part of the Milky Way or whether they were what were called island universes outside the Milky Way. The first person to prove that these galaxies were totally separate from the Milky Way was Edwin Hubble. Using the Cepheid variable stars I described in the last lecture, he attempted to calculate the distance to the Andromeda galaxy. Even though his numbers were somewhat off, he was able to prove that there was no way that Andromeda was part of the Milky Way. These same Cepheid variable stars also helped to determine that distant objects are accelerating away from us, which is part of the evidence for the Big Bang. We'll look at this more in the next lecture. Cepheid variables are a type of object called a standard candle. They are objects of known brightness that can be used to determine the distance to far-off objects. In the case of Cepheid variables, remember that the pulsation rate determines its brightness. Another type of standard candle is the type 1A supernova. This type of supernova explosion always explodes with the same brightness. Standard candles are important because if we know how bright an object actually is, we can compare that to how bright they look, and thus determine how far away the object is. Here's a more everyday example. Imagine you have a lamp with a 100-watt light bulb in it. If you stand very close to the bulb, it's quite bright. But if you start to walk back from the light, the farther away you get, the dimmer the bulb looks. The bulb is still putting out the same amount of light, but it looks dimmer because you are farther away. The same process helps us to determine the distance to galaxies that have these standard candles within them. The next thing we need to look at are galaxy shapes. There are three main types, and you should already be very familiar with one of them. Let's try to spot one of each type of this galaxy in the image of the Hubble Ultra Deep Field. In this image, everything you see is a galaxy. These aren't stars, but are far-off galaxies. Let's look at this image first. Can you tell what type of galaxy this is? Hopefully so. This is a spiral galaxy. This is more or less what the Milky Way looks like. There are two types of spiral galaxies, and we'll look at those in a moment. How about this one? There aren't any spiral arms here, but can you see that it is oval-shaped? This type of galaxy is called an elliptical. Some of them are more rounded, and some of them are more stretched out into a more oval shape. Now, how about this one? The picture is kind of small and hard to see, but hopefully you can tell that this is neither spiral nor elliptical shaped. This one has a rather obvious and simple name. The galaxies that are neither spiral nor elliptical are called irregular. Here are several images of galaxies. Can you tell that all three of the ones on the top are spirals? The first two are face-on spirals.
though the spiral arms are a little easier to see in the second one. The third is an edge-on spiral that we're looking at from the side. Notice this dark line across it. Remember, that is a dust lane where new stars are forming. And those are only seen in spiral galaxies. The two on the bottom left are ellipticals. The first one is pretty circular and the second one is a little more oval, stretched out in the left-right direction more than the up-down direction. The last image is of an irregular galaxy. It doesn't fit into either of the other categories.
This is a nice chart that shows Edwin Hubble's galaxy classification scheme. This is sometimes called the tuning fork diagram. All of the galaxies on the left are ellipticals. Elliptical galaxies are given the designation E0, E1, E2, E3, all the way up to E7, depending on how stretched out the oval is. E0 would indicate a completely round galaxy, while an E7 is the most stretched out oval. On the right side of the diagram, we have the spirals. Notice, though, that there are two different branches. The upper branch is what we call the regular spirals. They have a nucleus in the center, and the spiral arms come off the nucleus. The subtypes are SA, SB, and SC, and the difference between them is how tightly wound the arms are. In the SA, the arms are very tightly pulled into the nucleus, while the SC arms are more spread out. The lower branch are what we call barred spirals. These galaxies have a nucleus like regular spirals, but they also have a line or bar of stars that cuts through the nucleus. Then, the spiral arms come off of the ends of the bar. Notice the subtypes are SBA, SBB, and SBC, each representing a barred spiral, that's the SB part, with their arms spread more and more widely as you move from A to B to C. Remember that spiral galaxies are flattened disks with one or more spiral arms. Our Milky Way is a spiral, and more specifically, probably a barred spiral. Our solar system is located in one of the spiral arms. Also remember that the major components of spiral galaxies are the bulge in the center, the disk that surrounds the bulge, and the halo that is both above and below the plane of the galaxy. Here's an image of an edge-on SA galaxy. The spheroidal component is the bulge and the halo, and it's made mostly of very old stars without much gas. The disk, since it contains a lot of gas, has a lot of younger stars in addition to the older ones. Young stars form in the gas and dust in this disk.
Here's the same picture again on the left and another one on the right that is face on. Notice the dark dust lane across the edge-on galaxy and how tightly wound the arms are in the face-on galaxy. The new stars form in the emission nebula, the H2 regions.
Here are a couple of SB galaxies. These have spiral arms that are a little more loosely wound than the SA galaxies. The brighter regions you see, the H2 regions, are emission nebulae, where young stars are forming. Notice also the coloration in the lower image of the Andromeda galaxy. The bright center that's more yellow is indicative of those older population 2 stars, while the bluish areas in the disk are showing the presence of those larger, younger population 1 stars. Remember that even though the sun isn't blue, it's still a population 1 star. Here we see the most loosely wound of the regular spirals, the SC galaxy. Notice how the center portion of the galaxy is much more red and yellow than the spiral arms. The bluer stars in the spiral arms are much younger than the reddish stars in the center. These blue stars are fed by the gas clouds in the disk.
This doesn't mean that all stars in the arms are blue. Remember, our own sun is yellow and out in the spiral arm area, but the average star in the arms is younger, hotter, and bluer than the average star in the bulge.
Here's another SC galaxy. Notice here, the bulge is much less prevalent and the arms are much more widely spread. These types of galaxies have lots of active star-forming regions. Now, let's look a little more closely at the barred spiral galaxies. Can you see the long bar that goes through the galactic center? The spiral arms come off the ends of this bar. Here are images of each of the subtypes of the barred spiral. The SBA arms are tightly wound around the nucleus, while the B types and C types are more spread farther away from the nucleus. There is a special type of galaxy called a lenticular that is kind of like a hybrid between the ellipticals and the spirals. It has a disk like the spirals do, but with very little dust and gas like the ellipticals.
I'm not going to ask you about lenticulars on your assignment or on your exam, as they're kind of an in-between stage, but I wanted you to have seen an example. Here's another image of a lenticular, this time edge-on. Now, let's leave the spirals and move on to the ellipticals. More than half of all galaxies are ellipticals. They basically look just like massive blobs of stars. They can be more rounded or quite elliptical in shape. The ellipticals are much older than spirals and thus have very little gas and dust remaining. Because of this, they also have no new stars forming. Some ellipticals are enormous, but many are quite small. The most numerous galaxies in the universe are dwarf ellipticals. So the biggest and smallest galaxies are ellipticals, meaning that spirals are more middle-sized.
Here's an enlarged image of an elliptical. These galaxies are all bulge, just a large spheroid. There is no disk component to these galaxies.
Compare that image to the images of these four globular clusters. The major way you can differentiate the galaxy from the globular clusters is that in the galaxy, you can't differentiate individual stars throughout the structure because the galaxy is so far away. It just looks like uniform brightness. You can see lots of individual stars in the globular clusters.
Irregulars are those galaxies that do not fit into any of the other categories. They are just chaotic mixtures of stars, gas, and dust. These irregular galaxies are often found near other galaxies who are gravitationally distorting their shape. Here's another image of an irregular. No spiral arms, no regular oval shape, just a lot of random splotches around. The brighter blue-white area is a star-forming region. Here's another irregular galaxy, Messier Catalog Entry 82. This galaxy is probably a combination of two galaxies that have merged. The white portion was probably one galaxy, and the red part was another galaxy, and they are now in the process of combining and rearranging. Here is Hubble's tuning fork diagram again, this time with actual galaxy photos instead of the drawings. For the ellipticals, all you have is a spheroid. As you move to the left, they get more and more circular. For the spirals, the disk of spiral arms dominates the spherical nucleus in the center. As you move toward the left of this group, the arms are pulled in tighter and there is less dust and gas. Now time for a quiz. What type of galaxy is this? Hopefully, it's obvious that this is an elliptical. Nice round blob, no arms. How about this one? Hopefully this is easy too. This is definitely a regular spiral. The arms are present, but there is no bar through the center, so it is not a barred spiral. And this one? It has no spiral arms, and it's not an elliptical either. All we can see is a disorganized center with splotches of star-forming regions scattered around. This is an irregular.
So far, we've looked at lots of images of individual galaxies, but galaxies don't usually live alone. They almost always appear in larger structures consisting of multiple galaxies.
We use two different terms, group and cluster, to describe how many and what type the dominant galaxies in the set have. Spiral galaxies are often found in small groups of galaxies, up to a few dozen galaxies in each group. Here you see 3 large spirals with several smaller galaxies around. This group includes 3 large members: our Milky Way, M31, the Andromeda Galaxy, and M33, the Triangulum Galaxy. There are also lots of small galaxies called satellite galaxies that orbit around each of the larger ones. This is called our local group. While spirals are often found in small groups, ellipticals are found in huge clusters. Instead of dozens of galaxies that make up a group, typically hundreds or thousands of galaxies make up a cluster or a supercluster. Here we see a deep image of very distant galaxies. The farther away we're looking, the farther back in time we're seeing. This is a picture showing how the universe looked very long ago. This light has been traveling for a long time and is just now reaching us. So though the light is very old, the picture shows how the galaxies looked when they were very young. Since the Big Bang, which we'll talk more about in the next lecture, the universe has been expanding. In this graphic, you can see how the space between the galaxies continues to increase over time. In much the same way as the solar system developed from a nebula, a galaxy forms from an even larger cloud of material called a protogalactic cloud. These were made of hydrogen and helium, and the first stars that formed the first galaxies condensed out of this material. These first stars were enormous and thus didn't live for very long. Constant supernova explosions kept these gas clouds churning and not able to form stars. The leftover gas ended up settling out in a disk, much like a spinning ball of pizza dough stretches out into a disk. But if all galaxies start out the same way, why do they come out looking so differently? Some have arms and others don't, in addition to other differences. Think of regular clouds in the sky. They all form in similar ways, but no two clouds ever look identical due to the interaction of air molecules in the atmosphere. Similarly, the initial spin or rotation of the gas clouds will affect the size of the disk and how widely spread the material is. If the inward gravitational force is the stronger force, the gas cloud will contract more than it spins, creating an elliptical. If there isn't enough mass for the gravity to dominate, the spin will twist out the arms into a spiral. Additionally, those galaxies that formed in higher density regions of the protogalactic clouds were able to cool and form stars before their material was spread out into the disks that form in spiral galaxies. Some galaxies also have their shapes altered by galactic collisions. Here, individual stars probably don't collide very often due to large amounts of space between stars. But the shapes of the galaxies are dramatically altered as one galaxy passes through another, affected by the other galaxy's gravity. Here you see images of a couple different galaxy mergers at different times in our universe's past. You can see, especially in the upper center image, that it looks like the galaxy is getting stretched and ripped apart. On the left, you see another galaxy merger. The image on the right is the two galactic nuclei zoomed in. Look at how stretched out the arms from these two spiral galaxies are and how they're getting stretched apart. This may be how irregular galaxies are created, distorted by other galaxies. We use computer modeling to show how galaxies collide. Here is the first stage in a collision between two spirals. Here is the full series of images of how the two spiral galaxies might interact and combine over time. First, they start to slide through each other. Then, the arms get stretched out as the other galaxy's gravity pulls on the stars. Collisions might explain why elliptical galaxies are found where many galaxies are close together. They may have started out as spirals, but after colliding with other galaxies, they settled into simpler shapes. Gravity pulls the bodies together. Many giant elliptical galaxies actually seem to have eaten other galaxies when viewed in infrared light. What appears to be one galaxy actually has multiple galaxies within it, and it's ready to eat several more. We call this process galactic cannibalism. Using the Doppler effect, we can look at clusters of galaxies and determine how these galaxies are moving relative to one another. Some galaxies have what's called an active galactic nuclei, or AGN. This small region within the center of the galaxy is unusually active over some part or even over all of the electromagnetic spectrum. Galaxies are often classified as radio quiet or radio loud, depending on how much light in the radio wave part of the spectrum they are emitting. We assume that the radio loud galaxies have actively feeding supermassive black holes at their centers. Luckily, our Milky Way is radio quiet, with our supermassive black hole, Sagittarius A star, not actively feeding, or our galaxy would be a much more dangerous place. Radio loud galaxies are easy to detect from very far away due to the large amounts of energy they release. They sometimes actually have jets of material that shoot out from their nuclei. There is still a lot we do not understand about these active galactic nuclei. Many of these active galactic nuclei are quasars, or quasi-stellar radio sources. They are some of the most distant objects in the observable universe, and though they are small, they shine many times brighter than ordinary galaxies. They are thought to perhaps be disks of gas falling into a supermassive black hole. Again, there is still much we do not know about these distant galaxies, but over the coming years we will probably learn quite a bit more, perhaps finding out that some of what we currently believe to be true may be incorrect, or that it's only the tip of the iceberg of what remains to be discovered.
One thing we know for sure, though, is that these distant objects all have red-shifted spectral lines, which actually serves as a major piece of evidence for our last topic, the Big Bang Theory.